Welcome to the mechanics of rest. There is a question that sounds simple until you sit with it. The sun burns at nearly 6,000 degrees on its surface, hotter in its outer atmosphere, and hotter still in its core. Stars like it, and far larger than it, are scattered across the galaxy in their hundreds of billions. The universe is full of fire, and yet the space between those fires is colder than anything that exists naturally on Earth. Colder than the poles, colder than the upper atmosphere, colder than any temperature a human body has ever experienced and survived. Nearly 300 degrees below zero on a Celsius scale. Almost as cold as matter is capable of being. How does that happen? How can something be surrounded by sources of extraordinary heat and remain that cold? The answer is not simple, and it is not what most people assume. It runs through the nature of heat itself, what heat actually is, and the specific ways it is capable of moving, and it ends somewhere unexpected. In the first moments of the universe, and in a faint warmth that still fills every corner of space, even now. If this channel is new to you, Quiet Chronicles publishes weekly, long, unhurried science for late hours. A like and a subscription keep the channel growing, and they are appreciated more than the algorithm shows. The place to begin is not in space. It is in the hand, in the warmth of something held, and in the quiet physics of what that warmth actually is. Chapter 1: The Heat in a Held Hand. Heat announces itself before it is understood. A ceramic mug held between both palms on a cold morning, the warmth spreading into the skin within seconds. A metal spoon left in a bowl of soup, too hot to hold by the time the meal is finished. The stone floor of an unheated room in winter, drawing the warmth from a bare foot with a persistence that feels almost deliberate. These are not complicated experiences, and they do not feel like physics. They feel like comfort, or discomfort, or the simple evidence of temperature difference. But inside each of them, something specific is happening, something that took scientists the better part of 2 centuries to describe with any precision, and whose correct description turns out to be the first key to understanding why space is cold at all. What heat is, as a physical phenomenon, was genuinely unclear for most of the history of science. The dominant theory for roughly a century, from the mid-1700s through the early 1800s, held that heat was a substance. Not a metaphor for a substance, not a model that behaved as if heat were a substance, but an actual material fluid, weightless and invisible, that flowed from hot objects into cold ones and accumulated in matter the way water accumulates in a sponge. This fluid was called caloric. It was a reasonable hypothesis. It explained, with considerable success, why heat moved from a warm body to a cold one. The fluid flowed downhill, thermally speaking. It explained why mixing hot and cold water produced a temperature in between. It explained why some materials held heat better than others. They had a greater capacity for caloric. Antoine Lavoisier, one of the most careful and systematic chemists of the 18th century, included caloric as an element in his 1789 table of chemical elements, alongside oxygen and hydrogen. The theory was not fringe, it was consensus. Joseph Black, working at the University of Glasgow in the 1760s, did not set out to challenge the caloric theory. He was interested in a more specific and practical question: what happens to heat when ice melts? The experiment he conducted was careful and repeated. He took a quantity of ice at exactly 0 degrees Celsius and applied a steady, measured source of heat to it. The ice absorbed heat continuously. For a long time, a time far longer than intuition would suggest, the temperature did not rise. The ice melted, slowly and steadily, and the thermometer read 0 throughout, until the last of the ice had become water, at which point the temperature began to climb. The same quantity of heat that could have raised liquid water by 80 degrees was consumed entirely in the act of melting the ice, without moving the thermometer at all. This was a problem for caloric. If heat were a fluid accumulating in matter, and heat was being added continuously, the temperature should have been rising continuously. The fact that it was not, that heat could be absorbed without producing any change in temperature, meant that heat and temperature were not the same thing. Black named what he had found latent heat, heat that was present in a substance but hidden from the thermometer, absorbed into the change of state itself. His measurement put the latent heat of fusion for ice at approximately 80 calories per gram, a figure that remains accurate today. He did not know what latent heat was, in mechanical terms. He had no model for where the heat went when it disappeared into the melting ice, but he had demonstrated, precisely and reproducibly, that the caloric model was incomplete. What Black's experiment implied, but could not yet say directly, was that temperature measures something about the internal condition of matter, not the quantity of heat stored in it, but the intensity of something happening within it. The correct description of that something came later, built through the work of many hands across the 19th century, and it replaced the image of a fluid entirely. Heat, in the understanding that emerged, is not a substance at all. It is the aggregate kinetic energy of the particles that make up matter, atoms and molecules in constant motion, vibrating and rotating and translating through whatever space they occupy. Temperature is a measure of the average intensity of that motion. A hot object is one whose particles are moving fast. A cold object is one whose particles are moving slowly. When a warm mug transfers heat to a cool hand, what is happening at the level of atoms is that the faster moving molecules of the ceramic are colliding with the slower moving molecules of the skin, and energy is passing from the faster to the slower at each collision, gradually evening out the difference. This is not an easy thing to hold in the mind at first. The ordinary experience of heat, the warmth of a fire, the cold of ice against the wrist, does not feel like the behavior of invisible particles. It feels like a quality of the world, something that belongs to things rather than something happening inside them. But the particle picture makes predictions that the caloric model cannot. It explains why Black's ice absorbed heat without warming. The energy was going into breaking the bonds that held the water molecules in their crystalline arrangement, not into speeding up their motion. It explains why gases expand when heated. Faster moving particles push harder against whatever contains them. It explains, in terms that the caloric theory never could, why heat is produced by friction, not because caloric is being squeezed out of the material, but because the mechanical work of rubbing is being converted directly into molecular motion. At the center of this understanding sits a number that seems unremarkable until it is considered carefully. Water requires 4,184 joules of energy to raise 1 kilogram of its temperature by 1 degree Kelvin. This is its specific heat capacity, and it is unusually high, higher than most common substances. A kilogram of copper requires only 385 joules for the same change. A kilogram of lead requires 128. The difference matters practically. It is why a metal spoon heats up faster than the liquid it sits in, why stone floors lose their warmth to a foot faster than a wooden floor does, why the ocean moderates coastal climates. Each material has its own capacity for molecular motion, its own relationship between energy input and temperature rise, because each has its own internal structure and its own range of available motions at the molecular scale. Heat, then, is motion. Temperature is the average intensity of that motion. And heat moves from place to place through matter in two ways that depend entirely on the presence of matter, and one way that does not. The first is conduction. When the mug warms the hand, conduction is the mechanism. Molecules in the warm ceramic vibrating energetically, colliding with the molecules of skin at the boundary between them, passing kinetic energy across that boundary collision by collision. The rate at which this happens depends on how closely the molecules are packed and how freely they can pass energy along, which is why metals conduct heat so readily. They're free electrons carrying energy rapidly through the material, while wood and wool and still air conduct it slowly, their molecular structures offering far fewer pathways. Copper conducts heat at roughly 400 watts per meter per degree of temperature difference. Still air conducts at about 0.025 watts by the same measure, 16,000 times more slowly. Conduction needs contact. It needs molecules close enough to collide. Without matter, without those collisions, conduction does not occur. The second is convection. A pot of water heated from below circulates because the water near the heat source warms, expands slightly, becomes less dense than the cooler water above it, and rises, carrying its thermal energy upward with it as bulk movement of the fluid. Cooler water descends to take its place, is warmed, rises in turn. The same process drives weather. Warm air rising from sun-heated ground, cool air descending in its place. The circulation patterns that move heat around the surface of the planet in the enormous slow loops of atmospheric and oceanic current. Convection moves heat efficiently, but it requires a fluid, a gas or a liquid. to carry it. Without matter capable of bulk movement, convection is not available. These two mechanisms, conduction and convection, handle nearly all the heat transfer that human beings encounter in daily life. The warmth of a radiator spreading through a room, the heat of a stove conducted through a pan into food, the warm updrafts above a summer road, conduction and convection working through the matter that fills terrestrial environments. And this is precisely why space presents such an unusual thermal situation. Between the stars, between the planets, between the galaxies, matter is so vanishingly sparse, measured in individual atoms per cubic centimeter, or in some regions per cubic meter, that conduction and convection effectively do not operate. The molecular collisions required for conduction are rare almost beyond reckoning. The bulk fluid movement required for convection has nothing to flow. This leaves heat transfer in space to the third mechanism, the one that does not require matter at all. But before arriving at that mechanism, it is worth pausing on the nature of vacuum itself, because the ordinary image of space as simply empty turns out to be considerably less accurate than the physics requires. What actually fills the space between stars, and why it fails to carry heat in any meaningful way, is the next part of the question the title poses. The answer begins not in space, but in a courtyard in Germany in 1654, with a blacksmith's copper bowls and a crowd of watching dignitaries, and a demonstration that no one present fully understood. Chapter 2: The Mathematics of Warmth Moving. Benjamin Thompson was not, by most accounts, a likable man. He was born in Massachusetts in 1753, worked as a British loyalist spy during the American Revolution, abandoned his wife and daughter when he fled to England, and spent the subsequent decades accumulating titles and enemies in roughly equal measure. He became Count Rumford of the Holy Roman Empire through service to the Bavarian government, reorganized Munich's poor relief system with a coldness that bordered on contempt for its recipients, and feuded with nearly every scientific institution he encountered. He also, almost incidentally, performed one of the most consequential experiments in the history of thermodynamics, not because he was searching for a theory of heat, but because he was supervising the manufacture of cannons and noticed something that refused to fit the prevailing explanation. The year was 1798, and Thompson was overseeing artillery production at the Munich arsenal. Cannon barrels were bored from solid bronze cylinders using a rotating drill, a blunt, heavy tool driven by horsepower, cutting slowly through the metal. The process generated substantial heat, which was expected. Caloric theory held that the mechanical action of cutting released caloric fluid that had been stored in the metal. What Thompson noticed, and then measured, was that the heat generated did not diminish as the boring continued. A sharp drill, cutting efficiently and producing fine metal shavings, generated heat. A blunt drill, barely cutting at all and producing almost no shavings, generated at least as much heat, possibly more. He suspended the barrel assembly in a tank of water and measured the temperature rise. With a deliberately blunted drill that could not cut, the water reached boiling in roughly 2.5 hours and showed no sign of stopping as long as the horse continued to turn the mechanism. This was not compatible with caloric. If heat were a fluid stored in the metal, cutting should have released it, but the blunt drill was releasing more heat than the sharp one while removing less material, and the process showed no limit. Heat continued to be produced for as long as mechanical work was applied, with no depletion of the source. Thomson concluded, in a paper he presented to the Royal Society, that heat could not be a material substance with a fixed quantity stored in matter. Something was being converted, the mechanical work of the horses, into heat, without any material substance changing hands. He called it, cautiously, the heat excited by friction, and he was correct in his instinct even if he lacked the vocabulary to name what was happening at the molecular level. The cannon boring experiment did not immediately overturn the caloric theory. Lavoisier's framework was too well established for a single demonstration to dislodge it, but it planted a specific and ultimately fatal anomaly at the center of the model. The mathematical framework that would eventually replace caloric came not from a metallurgist in Bavaria, but from a mathematician in France. Joseph Fourier spent years on the problem of heat conduction, not the question of what heat was, but the question of how it moved through solid materials, and whether its movement could be described by equations precise enough to make predictions. His answer, published in 1822 in the Théorie analytique de la chaleur, was yes, and the equations he produced remain in use today, 2 centuries later, essentially unchanged. Fourier showed that the rate at which heat flows through a material is proportional to the temperature gradient across it. The steeper the temperature difference between one side and the other, the faster heat moves from warm to cold. He showed that each material has a characteristic value, what we now call thermal conductivity, that determines how readily it transmits that flow. And he developed the partial differential equations that describe how temperature evolves through a body over time as heat moves through it. Fourier's thermal conductivity is a number that varies enormously across materials, and that variation tells the story of conduction more vividly than any description. Copper, whose free electrons carry energy through the lattice with minimal resistance, conducts heat at approximately 400 watts per meter per Kelvin, meaning that across a 1 meter bar of copper, a temperature difference of 1 degree drives 400 watts of heat flow. Iron conducts at roughly 80 watts by the same measure, glass at about 1, wood at 0.1 to 0.2, depending on its density and grain. Still air at 0.025, 16,000 times more slowly than copper, because the air molecules are widely spaced and pass energy between them only through occasional collision, with no connected solid lattice to carry it. The practical consequence of this range is visible in the world. A metal handle on a hot pan becomes dangerously warm in seconds. A wooden handle on the same pan remains comfortable to hold. A down jacket traps still air in its structure and uses the air's poor conductivity as insulation. A stone floor on a cold morning feels colder than a wooden floor at the same temperature because stone's higher conductivity pulls heat from the foot faster. The implication for vacuum runs directly from Fourier's framework. Thermal conductivity is a property of material. Vacuum has no material. There is no lattice of atoms to pass energy along, no free electrons to carry it, no molecular collisions to transfer it. The thermal conductivity of vacuum is not low. It is undefined because the concept does not apply. Conduction, in the absence of matter, does not merely slow down, it does not occur. Convection completes the picture of what vacuum excludes, where conduction moves heat through matter by molecular vibration, energy passing from particle to particle through contact. Convection moves heat by the bulk physical displacement of matter itself. Warm fluid rises because thermal expansion makes it less dense than the cooler fluid around it. Cooler fluid descends to replace it. The circulation carries heat from the warm source upward and distributes it through the volume. Inside the sun, convection is a dominant mechanism for moving energy outward from the radiative zone toward the surface. Enormous columns of plasma rise from the interior, shed their energy at the photosphere, cool, and descend again in a pattern visible on the solar surface as granulation, a churning texture of bright rising cells and darker cooling edges, each cell several hundred kilometers across, rising and falling on timescales of minutes. On Earth, convection governs the large-scale movement of heat through the oceans and atmosphere, through the mantle of the planet, and through every boiling pot of water in every kitchen. For convection to carry heat, bulk matter must be able to move. In a vacuum, there is no bulk matter. The mechanism is not available. A body placed in interstellar space cannot lose heat to its surroundings through convection, because there is no surrounding fluid to convect into. It cannot lose heat through conduction for the same reason. Whatever heat exchange it undergoes must proceed entirely through the third mechanism, the one that Thomson's cannon borer and Fourier's equations said nothing about, because it operates on entirely different physical principles. Sadi Carnot, working in Paris in the early 1820s, was thinking about engines, specifically about how much work could be extracted from a heat difference, and whether there was a theoretical limit to the efficiency of that extraction. He died young, at 36, without knowing whether his framework was correct, and his work was largely ignored for 2 decades before Kelvin and Clausius recognized its significance and built thermodynamics on its foundation. Carnot's contribution was not to the question of how heat travels, but to the question of what heat fundamentally is: a difference, a gradient, something that only has meaning between 2 temperatures and that drives processes by moving toward equilibrium. The universe, in the thermodynamic picture that emerged from his work, is always moving toward a state in which temperature differences have been smoothed out, in which heat has distributed itself as evenly as the available mechanisms allow. That drive toward equilibrium is why heat moves from hot to cold and never spontaneously from cold to hot. It is why a warm object in a cold environment will always cool, and why the cooling will continue until the temperature difference is gone. In a material environment, conduction and convection handle most of this work. They move heat through the matter that surrounds objects and connect bodies at different temperatures through the shared medium. But between the stars, where that shared medium is absent, the drive toward equilibrium still exists. The physics has not changed, and only the third mechanism remains to carry it out. That third mechanism is older than matter. It operated before the first atoms formed, when the universe was a plasma too dense and too hot for light to travel freely through it. It travels at the fastest speed the universe permits. It requires nothing to move through, because it does not move through anything. It moves as a disturbance in the electromagnetic field itself, carrying energy across any distance, through any vacuum, arriving at whatever surface it encounters with the same energy it left its source with, diminished only by the geometry of how far it has spread. The story of how that mechanism was understood, and of the men who built the mathematics to describe it, begins not with heat at all, but with magnets, and with a Scottish physicist who spent years filling notebooks with diagrams of invisible lines of force that he believed connected every charged object in the universe to every other. Chapter 3: What the Thermometer Finds in Space. Before asking why space is cold, it is worth asking what cold means in space, because the answer is less straightforward than it appears, and the difficulty of answering it precisely reveals something important about the nature of temperature itself. On Earth, measuring the temperature of a substance is a matter of placing a thermometer in contact with it and waiting for equilibrium. The thermometer's working fluid, or its electrical resistance, or its expansion coefficient, responds to the molecular motion of the surrounding material and settles at a reading that reflects the average kinetic energy of those molecules. This works because the surrounding material has molecules, because there is matter present in sufficient density to come into thermal contact with the instrument, to collide with it repeatedly, to bring it to the same state as itself. In space, that condition is not reliably met. The question of what temperature space has depends entirely on which aspect of space you are measuring, and the answers differ from one another by factors of millions. The interstellar medium, the gas and dust that fills the space between stars within a galaxy, is not empty, though it is extraordinarily sparse by any terrestrial standard. Its average density across the Milky Way runs to approximately 1 hydrogen atom per cubic centimeter. To put that against something familiar, the air in a room at sea level contains roughly 2.7 Ti-1019 molecules per cubic centimeter, a number so much larger that the comparison barely registers as a comparison. The interstellar medium at its average density is, by any practical measure, a vacuum, but it is not nothing, and it has a temperature, or rather, it has several temperatures, depending on which phase of it is being measured. Cold molecular clouds sit at the low end of the interstellar temperature range. These are the densest regions of the interstellar medium, where hydrogen has combined into molecular form and dust grains have accumulated enough to shield the interior from the radiation that would otherwise heat and dissociate the molecules. Their temperatures run between 10 and 30 Kelvin, 10 to 30 degrees above absolute zero. They are cold enough that some molecules freeze onto the surfaces of dust grains, building thin, icy mantles of water, carbon monoxide, and methanol. They are also, somewhat paradoxically, the regions where stars form. The cold allows gravity to overcome the thermal pressure that would otherwise prevent collapse, and over millions of years, portions of these clouds condense into protostars. The coldest places in the galaxy are in a sense, the nurseries of its hottest objects. The warm neutral medium occupies a different thermal register entirely. Here, hydrogen exists as individual atoms rather than molecules, heated by the general radiation field of the galaxy to temperatures between 6,000 and 10,000 Kelvin. This is warmer than the surface of some cool stars, yet the density is still so low, a fraction of an atom per cubic centimeter, that the thermal energy contained in any reasonable volume is negligible. Temperature, in this context, is a measure of how fast individual particles are moving, not of how much energy is available to heat anything. A cubic meter of the warm neutral medium, despite its 10,000 Kelvin temperature, contains so little matter that its total thermal energy would not warm a cup of water by a measurable fraction of a degree. Hotter still is the hot ionized medium, plasma heated to temperatures between 100,000 and several million Kelvin by the shock waves of supernova explosions propagating through the galaxy. This is the material that fills the large bubbles carved out of the interstellar medium by dying massive stars, and it occupies perhaps half the total volume of the galaxy's disk. Its temperatures exceed those of stellar surfaces. Its density is lower still, often below 1/10,000th of an atom per cubic centimeter. The same paradox applies. More acutely, the hottest gas in the galaxy carries the least thermal energy per unit volume, because there is so little of it. A spacecraft passing through the hot ionized medium would not be heated by it in any meaningful sense, despite the million-degree temperature of the surrounding plasma, because the rate of molecular collision between the sparse plasma and the spacecraft's surface would be too low to transfer significant energy. This distinction between the temperature of a gas and the thermal energy it can deliver is one of the places where the physics of space most sharply departs from everyday intuition. On Earth, high temperature and high thermal energy go together because matter is dense enough that both scale together. In space, they can be entirely decoupled. The temperature of a particle tells you how fast it is moving. The thermal energy available in a region tells you how many such particles are present. The hot ionized medium has fast particles and almost none of them. The cold molecular cloud has slow particles and relatively many. A body placed in the hot ionized medium would not be cooked. A body placed in the cold molecular cloud would cool toward the ambient temperature of its surroundings, slowly, over a very long time. The temperature that a real object, a spacecraft, a rock, a dust grain, eventually reaches in interstellar space is its equilibrium temperature. The temperature at which the energy it absorbs from its surroundings exactly balances the energy it radiates away. Far from any star, the dominant energy input is the ambient radiation field of the galaxy, the combined light of all its stars, diluted by distance, plus the contribution of a specific and pervasive radiation field that fills the entire universe equally in every direction. In the outer regions of the solar system, beyond the influence of the sun, this equilibrium temperature for a dark body settles somewhere between 4 and 40 Kelvin, depending on the object's reflectivity and the local radiation environment. Deep in intergalactic space, far from any galaxy, it converges on a number that is precisely measured and physically significant: 2.725 Kelvin. That number is not arbitrary. It is not the equilibrium temperature set by the combined radiation of distant galaxies, though their contribution exists. It is the temperature of a radiation field that fills the entire observable universe, a field that was not produced by stars at all, and whose origin lies in the first few 100,000 years of cosmic history. Its discovery was one of the most consequential accidents in 20th century astronomy, and the instrument that found it was not built to look for it. Arno Penzias and Robert Wilson encountered it in 1964 at a horn-shaped antenna in Holmdel, New Jersey, that had been designed for satellite communication. The signal they found, a faint, uniform microwave hiss arriving with equal strength from every direction in the sky, would eventually be understood as the oldest light in the universe. But in the months before that understanding arrived, it was simply a persistent noise that refused to go away, and the two men worked methodically through every possible instrumental explanation before accepting that what they were measuring was real. The full story of that antenna and what the signal it found represents belongs to a later part of this account. What matters here is the measurement itself, space, at its baseline, away from the influence of any individual star or galaxy, has a temperature. It is 2.725 Kelvin. It is not zero. But knowing that space has a temperature does not yet explain why that temperature is so far below the temperatures of the stars that fill it. The stars are radiating continuously. They are pouring energy outward in every direction. The mechanisms that have been named so far, conduction and convection, are absent in vacuum, which accounts for part of the answer. But radiation, the third mechanism, operates in vacuum perfectly well. Stars radiate. That radiation crosses space. It arrives at whatever surfaces it encounters. The sun's radiation reaches Earth and warms it. Why does it not warm the space between here and there? Why does that space remain cold? The answer lies in how radiation behaves as it travels, in the geometry of how energy spreads across distance, and in the relationship between an object's temperature and the spectrum of radiation it emits. That relationship was worked out over the course of the 19th century by a series of physicists whose names are now attached to the laws they derived, and the most important of them, the one who finally brought the mathematics into agreement with the measurements, at the cost of introducing an idea so strange that he spent years hoping it was not physically real, was working in Berlin at the very end of 1900. Before arriving there, though, it is worth pausing on the mechanism itself, on what electromagnetic radiation actually is, how it was shown to exist, and what it means to say that something travels through vacuum without requiring anything to travel through. Chapter 4: The Third Mechanism. James Clerk Maxwell was 34 years old when he submitted the paper that unified electricity and magnetism into a single theoretical framework and, almost as a byproduct, predicted the existence of electromagnetic waves traveling through empty space at a fixed and calculable speed. The paper was called A Dynamical Theory of the Electromagnetic Field, and it was published in 1865. Maxwell had spent years filling notebooks with mechanical analogies, rotating vortices in an invisible medium, idle wheels between them transmitting force from one region to the next, not because he believed the machinery was real, but because he needed a scaffolding on which to hang the mathematics until the mathematics was strong enough to stand alone. When he finally stripped away the scaffolding, what remained were 4 equations describing the behavior of electric and magnetic fields, and a prediction that followed from them with the inevitability of geometry. A changing electric field produces a changing magnetic field, which produces a changing electric field, which propagates outward through space as a self-sustaining wave at a speed determined by 2 measurable constants of electricity and magnetism. Maxwell calculated that speed from those constants and obtained a number very close to the measured speed of light. The agreement was too precise to be coincidence, and he stated his conclusion directly. Light is an electromagnetic wave, not analogous to one, not behaving like one. It is one. The same oscillating field disturbance that his equations predicted would propagate through vacuum at 299,792 kilometers per second was the thing that illuminated rooms and cast shadows and bent through glass lenses. And if light was an electromagnetic wave, then the visible spectrum was merely a narrow band within a much wider range of possible frequencies, all of which should behave by the same laws, all of which should travel at the same speed, and most of which had never been detected because no instrument had been built to detect them. Maxwell died in 1879 at 48, before any of those other frequencies had been experimentally confirmed. The confirmation came from a laboratory in Karlsruhe, Germany, in the winter of 1887 and 1888, through the work of Heinrich Hertz, a physicist who had initially been skeptical that the predicted waves could be detected with available equipment and who undertook the experiment partly to settle his own doubts. His apparatus was elegant in its simplicity. On one side of the laboratory, a spark gap transmitter, 2 metal rods connected to an induction coil, with a small gap between their inner ends. When the coil discharged, a spark jumped the gap, and the rapid oscillation of charge produced an electromagnetic wave radiating outward from the transmitter. On the other side of the room, a receiver, a loop of wire with its own small gap, sized to resonate at the same frequency as the transmitter. When the transmitted wave reached the receiver, It induced an oscillating current in the loop, and a faint spark appeared across the receiver gap, visible evidence that energy had crossed the room as an electromagnetic wave through the air, without any conducting connection between the two instruments. Hertz mapped the waves. He reflected them from metal sheets and measured the interference patterns where outgoing and reflected waves overlapped, determining the wavelength directly. He showed that they could be polarized, oriented in a specific direction, just as Maxwell's theory predicted for transverse waves. He measured their speed and found it consistent with the speed of light. He demonstrated refraction through a prism made of pitch. In 2 years of careful work, he confirmed every major prediction that Maxwell's equations had made about electromagnetic radiation, and he did it at a frequency of roughly 50 megahertz, what would now be recognized as the radio band, lying far below visible light in frequency, far above it in wavelength, and entirely invisible to any human sense. When a student reportedly asked Hertz what practical applications his discovery might have, he is said to have replied that there were none, that he had simply confirmed a theoretical prediction, and that was the end of it. He died in 1894 at 36. Within a decade of his death, Marconi had transmitted a radio signal across the Atlantic Ocean, and the technology built on Hertz's useless waves was in the process of becoming the foundation of global communication. What Hertz demonstrated, and what Maxwell's theory had predicted, is that electromagnetic radiation does not require matter to propagate. This is the crucial fact for understanding heat transfer in space, and it is worth dwelling on what it actually means. A sound wave is a mechanical disturbance. It moves by compressing and rarefying the medium through which it travels, and without a medium, it does not travel at all. This is why space is silent, not metaphorically silent, but physically silent, because the pressure variations that constitute sound have nothing to propagate through. An electromagnetic wave is different in kind. It is a disturbance not in a material medium, but in the electromagnetic field itself, a field that permeates all of space, that exists in vacuum as fully as it exists in air or glass or metal. The wave propagates by the mutual induction of electric and magnetic components, each generating the other as they oscillate, and the process requires no supporting material. It crosses vacuum not despite the absence of matter, but indifferently to it. This is why radiation from the sun reaches Earth across 150 million kilometers of near-perfect vacuum without losing energy to the intervening space. There is no intervening medium to absorb it. The photons that left the solar surface travel outward, and whatever they encounter, a planet, a dust grain, a gas molecule, they interact with. Whatever they do not encounter, they pass through, or rather passed, without interaction. The vacuum between source and receiver is not a barrier that radiation overcomes. It is simply not a factor in the propagation. The connection to heat is direct. Every object with a temperature above absolute zero emits electromagnetic radiation. This is not a special property of hot objects. It is a universal consequence of the fact that charged particles in motion generate electromagnetic fields, and all matter above absolute zero contains charged particles in motion. A human hand at body temperature emits infrared radiation continuously. A block of ice emits infrared radiation, less intensely. The surface of the sun emits radiation across the visible spectrum and beyond. A dense cloud of gas at 10 Kelvin emits microwave radiation. The spectrum of that emission, the distribution of energy across frequencies, depends on the temperature of the emitting object, and the relationship between temperature and spectrum was one of the central problems in physics in the final decades of the 19th century. Gustav Kirchhoff had established, in the 1850s and 1860s, two laws that defined the theoretical framework. The first, a body in thermal equilibrium absorbs and emits radiation at every frequency at the same rate, so that its temperature remains constant. The second, the ratio of emitted to absorbed radiation at any frequency is the same for all bodies at a given temperature, which implied the existence of a universal function, a single curve describing the ideal emission spectrum as a function of temperature and frequency, independent of what the emitting material was made of. He named the idealized perfect emitter and absorber a black body, because a perfect absorber of all radiation would appear black, and he challenged his contemporaries to find the mathematical form of the blackbody radiation curve. The challenge occupied the best experimentalists and theorists in physics for the next 4 decades, resisted every classical approach, and was finally solved at the cost of breaking classical physics by a careful and conservative man in Berlin who did not entirely believe his own answer. That answer changed everything that followed, and it contains within it the precise mathematical reason why space between the stars remains cold despite their continuous output of radiation. The reason is geometric, and it is merciless. Radiation leaving a star spreads outward in all directions simultaneously, covering an ever-expanding sphere of space. The total energy in that radiation is conserved. Nothing absorbs it in the vacuum, but it is distributed across a surface that grows as the square of the distance from the source. At twice the distance, the same energy is spread over 4 times the area. At 10 times the distance, 100 times the area. At the distance of the nearest star to the sun, about 4.2 light years, or roughly 40 trillion kilometers, the flux of solar radiation has decreased by a factor of approximately 1.7 × 10^13 compared to its value at Earth's distance. Whatever energy arrives at that distance from the sun is, for all practical purposes, negligible. This inverse square dilution is not a failure of the radiation. The photons arrive with the same energy they left with, but so few of them arrive per unit area per unit time that a body placed at that distance would absorb almost nothing from the sun specifically, and its temperature would be set almost entirely by other sources. The combined diluted radiation of all the other stars in the galaxy, and the pervasive background field that fills the universe from every direction. The equilibrium temperature that results is far below anything in human experience, and the reason it is not absolute zero, the reason there is any warmth at all in the deepest spaces between galaxies, is the subject that will occupy the later chapters of this account. But the inverse square law is only part of the story of why radiation fails to warm interstellar space significantly. The other part lies in the specific relationship between temperature and the spectrum of emitted radiation, in the precise way that the energy leaving a hot object is distributed across frequencies, and what that distribution means for how efficiently a cold body in space can absorb it. That relationship, and the strange mathematical move required to describe it correctly, belongs to Max Planck, and to a Tuesday evening in October 1900, when he wrote down a formula he could derive but could not yet explain. Chapter 5: Almost Nothing. On the 8th of May 1654, in the market square of Magdeburg, a crowd of citizens and dignitaries watched Otto von Guericke attempt to pull apart two copper bowls. The bowls were hemispheres, each roughly 50 centimeters across, machined to fit together at their rims. A leather gasket greased with lard helped to seal the joint. Guericke had spent years developing an air pump, a device for removing air from an enclosed space, and he had used it to evacuate the interior of the joined hemispheres. He removed air until the pressure inside was approximately 1/15 of the surrounding atmosphere. The result was that the air pressing inward on the outside of the copper shell held the two halves together with a force that no human hand could overcome. Guericke attached teams of horses to each hemisphere. The accounts vary between 8 and 15 horses per side, and drove them in opposite directions. The hemispheres did not separate. The crowd, which had presumably expected the demonstration to be straightforward, watched the horses strain and the copper bowls hold. They understood, perhaps for the first time in a visceral and undeniable way, that the air surrounding them had weight and pressure, that its absence created a condition fundamentally different from its presence, and that the space inside those copper bowls was something that had to be actively created and maintained against the constant insistence of the atmosphere to refill it. What Guericke had made was not a perfect vacuum. It was a near vacuum, a space from which most, but not all, of the air had been removed, with a residual pressure roughly equal to what the air exerts at an altitude of about 50 kilometers above sea level. Robert Boyle, working in Oxford with his own improved air pump in the years following Guericke's demonstration, refined the technique. He used it to investigate the properties of the low-pressure space his pump produced. He showed that sound could not propagate through it. A bell suspended inside an evacuated glass jar rang silently, the clapper striking the metal without producing any audible tone outside the glass. He showed that animals placed inside it lost consciousness and died. He showed that flames were extinguished. Each of these results pointed toward the same conclusion, that the air surrounding ordinary objects was not a neutral backdrop, but an active physical medium. Its removal produced a qualitatively different state of affairs, one in which the mechanisms that depended on it, sound propagation, combustion, respiration, simply ceased to operate. The word vacuum comes from the Latin for empty, and for several centuries that etymology governed the conceptual framework. A vacuum was where nothing was. The philosophical objections to this were ancient. Aristotle had argued that nature abhors a vacuum, that empty space was a logical impossibility, and that any apparent void would immediately be filled. The experimental work of Guericke and Boyle refuted those objections in practice without entirely displacing the intuition behind them. The intuition that vacuum means nothing persists in everyday language and in the ordinary image of outer space. Outer space is often seen as a pure emptiness, a void into which objects are placed. That image is not merely imprecise. It actively misrepresents what the physics describes, and the misrepresentation matters for understanding how heat behaves there. Interstellar space is not empty. It is a physical medium with measurable properties, a density, a temperature structure, a chemical composition, a magnetic field, and a radiation environment. The interstellar medium consists primarily of hydrogen and helium in proportions that reflect the nucleosynthesis of the early universe. Trace quantities of heavier elements and complex molecules are concentrated in the denser cold regions. Its average density across the disk of the Milky Way is approximately 1 hydrogen atom per cubic centimeter. This is a number that sounds almost like nothing until it is placed against the density of intergalactic space. In intergalactic space, the average density drops to roughly 1 particle per cubic meter. The difference between 1 atom per cubic centimeter and 1 atom per cubic meter is a factor of 1 million. It corresponds to a real physical distinction. The interstellar medium, however sparse, has enough material to support chemistry, to carry magnetic fields, to form stars over geological timescales. The intergalactic medium is so close to a true vacuum that it approaches the limit the physics allows. Even that limit is not zero. The quantum vacuum, the base state of space in the absence of all matter and radiation, is not a condition of absolute nothingness. It is a condition of minimum energy, and that minimum is not zero. Quantum field theory, which describes the behavior of particles and fields at the fundamental level, requires that every field permeating space fluctuates continuously. Even in its lowest energy state, the electromagnetic field and the fields associated with every particle type are active. These fluctuations are not material particles in any lasting sense. They are transient, arising and vanishing within the constraints set by the uncertainty principle. This permits brief violations of energy conservation, provided they resolve quickly enough. The vacuum in this description is not still. It hums with activity that has no classical analog, a seething of virtual processes that leave no net matter or radiation behind, but that have real, measurable physical consequences. One of those consequences was predicted by the Dutch physicist Hendrik Casimir in 1948, and it is among the most precise confirmations of quantum field theory ever achieved. Casimir showed that if 2 flat metal plates were placed very close together in a vacuum, within a fraction of a micrometer, they would experience a tiny attractive force. This occurs with no electrical charge and no gravitational explanation. The mechanism is subtle. Between the plates, only electromagnetic fluctuations whose wavelengths fit within the gap can exist. The geometry suppresses the others. Outside the plates, fluctuations of all wavelengths are present. The result is a slight excess of radiation pressure from outside compared to between, and the plates are pushed together by the imbalance. The force is extraordinarily small, measurable only with instruments capable of detecting forces in the range of fractions of a micronewton. But it is real, and it has been measured with increasing precision since Steve Lamouro's landmark experiment in 1997. This confirms that the vacuum between the plates is not inert. It has a physical structure that geometry can modify. The thermal implications of this are limited, but not trivial. The quantum vacuum does not carry heat in any conventional sense. It has no temperature, because temperature is a property of matter in thermal equilibrium. The vacuum contains no matter, but it is not a passive backdrop to thermal physics. The radiation that fills space, the pervasive background field that sets the baseline temperature of the universe, propagates through the quantum vacuum. It interacts with whatever matter it encounters and is shaped by the field structure of the space it crosses. The distinction between the quantum vacuum and the near vacuum of interstellar or intergalactic space is the distinction between a theoretical floor and a physical reality. The actual spaces between and within galaxies contain matter and radiation at specific densities and temperatures. Those quantities are measurable, variable, and consequential. What the vacuum, at any level of approximation, reliably excludes is conduction and convection. Conduction requires a connected medium of atoms or electrons through which energy can pass by proximity and collision. Even the interstellar medium at 1 atom per cubic centimeter is sparse. The mean free path of a particle, the average distance it travels before colliding with another, runs to tens of astronomical units in warm regions. In hot, diffuse regions, it can reach thousands of astronomical units. The rate of collision between particles is so low that thermal conduction across any macroscopic distance through the interstellar medium is negligible. Convection requires bulk fluid flow, which requires a density and a pressure gradient large enough to drive circulation. The interstellar medium does not possess these on scales relevant to heat transfer between objects. A spacecraft in interstellar space is thermally isolated from its surroundings in a way that has no terrestrial analog. It is not because it is surrounded by an insulating material, but because there is nothing substantial enough to connect it thermally to anything else. Jan Oort spent much of his career mapping the structure of the Milky Way's interstellar medium. His name is attached to the distant reservoir of comets that surrounds the solar system at the edge of the sun's gravitational influence. He traced the relationship between its different phases, the cold clouds, the warm neutral gas, and the hot ionized bubbles. His work established that the interstellar medium is not uniform but structured. It is organized by the interplay of stellar radiation, supernova shock waves, gravity, and magnetic fields into a complex ecology of regions at vastly different temperatures and densities. That complexity does not change the fundamental thermal isolation of objects within it. It does mean that the thermal environment of interstellar space varies considerably from one region to another. A dust grain in a cold molecular cloud sits in a radiation environment very different from a dust grain in the hot ionized medium. Its equilibrium temperature reflects that difference. None of this complexity, however, changes the basic answer to why vacuum is cold. The mechanisms that move heat efficiently, conduction and convection, are absent. The mechanism that remains, radiation, operates across all distances but spreads its energy over an ever-expanding geometry. It delivers diminishing flux at increasing distances from any source. The interstellar medium, however structured and however varied, is too sparse to compensate for the absence of the contact-based mechanisms. What heat a body in space carries, it carries largely alone. It exchanges that heat with its surroundings only through the slow currency of electromagnetic radiation. That radiation, and the specific laws governing how it is emitted and absorbed, will determine the equilibrium temperature of anything placed in space. Those laws connect temperature to spectrum in a precise and quantitative way. They rest on the work of a small group of physicists in the last decades of the 19th century. One of them introduced, reluctantly and without fully understanding what he was doing, the concept that would eventually become quantum mechanics. He had been working on the problem for years, trying formula after formula, each one fitting part of the experimental data and failing at the extremes. Then, one evening in October 1900, he wrote down a new expression that fit all of the data. He realized, in deriving it, that he had been forced to assume something about the nature of energy. It was something that had no place in classical physics, and that he could not explain. Chapter 6: The Color of Heat. Something happens to iron when it is heated slowly and steadily from room temperature. For a long time, nothing visible changes. The metal absorbs energy, its temperature rises, and it looks exactly as it did before. Then, at around 480 degrees Celsius, something shifts. A faint red glow appears, barely distinguishable from the surrounding darkness, the color of an ember almost spent. As the temperature climbs further, the glow deepens and brightens, a fuller red, then orange, then a yellow that begins to carry hints of white. At temperatures above 1,000 degrees, the metal glows with a light bright enough to read by, a warm yellow-white that shifts progressively toward blue-white as the heat continues to climb. Blacksmiths learned to read this progression centuries before anyone understood what caused it. The color of heated metal was a practical thermometer, a way of knowing the temperature of the forge by watching the light it produced. What no one understood for all those centuries of practical use was that the iron was not merely glowing. It was doing something far more specific. It was broadcasting a precise record of its own temperature. This record was encoded in the distribution of colors in the light it emitted, readable by anyone who knew the key. The key took most of the 19th century to find. Its final form required breaking an assumption so fundamental to classical physics that the man who broke it spent years hoping the break was not real. The connection between heat and light had been noticed long before it was understood. William Herschel demonstrated in 1800 that the sun's radiation extended beyond the visible red end of the spectrum. He placed thermometers at successive positions across a solar spectrum produced by a glass prism. He found that the temperature reading continued to rise even after the thermometer had moved past the last visible red light. It moved into a region where no color was visible at all. He had found infrared radiation without naming it as such, and without understanding that it was the same kind of phenomenon as visible light at a different frequency. The connection between the two came only with Maxwell's theory in 1865 and Hertz's confirmation 2 decades after. It was the recognition that visible light, infrared, and radio waves were all manifestations of the same electromagnetic phenomenon. Gustav Kirchhoff had posed the theoretical challenge in 1859. Describe mathematically the spectrum of radiation emitted by a perfect absorber at a given temperature. The perfect absorber, which he called a blackbody, was a theoretical idealization. It was a surface that absorbed all radiation falling on it at every frequency and reflected none. Real materials are imperfect absorbers. They reflect some frequencies and absorb others, which is why objects have colors. The blackbody was the clean theoretical case. Kirchhoff's radiation laws established that its emission spectrum was a universal function. It was the same for all blackbodies regardless of their material composition, dependent only on temperature. Find that function, and you would have a complete description of how heat and radiation were connected. The experimental data accumulated through the 1870s and 1880s. Joseph Stephan established in 1879 from measurements that the total power radiated by a hot body scaled as the fourth power of its absolute temperature. Double the temperature and the radiated power increases by a factor of 16. Ludwig Boltzmann derived this result theoretically from thermodynamic principles 4 years later. The relationship became the Stefan-Boltzmann law, carrying both their names. Wilhelm Wien showed in 1893 that the peak frequency of the blackbody spectrum shifted with temperature in a precise and simple way. As temperature increased, the peak moved toward higher frequencies and shorter wavelengths. At the temperature of a wood fire, the peak sits in the infrared, and the visible glow is the high-frequency tail of the distribution. At the temperature of the solar surface, approximately 5,778 Kelvin, the peak falls at roughly 502 nanometers in the green portion of the visible spectrum. The sun does not appear green because it emits so broadly across the full visible range that the eye and brain integrate the mixture as white. Wien's formula described the peak correctly, but it failed at low frequencies. Lord Rayleigh approached the problem from classical statistical mechanics and produced a formula that worked at low frequencies, but it failed catastrophically at high frequencies. His formula predicted that a blackbody should emit infinite energy at short wavelengths. This was physically absurd and became known, with characteristic British understatement, as the ultraviolet catastrophe. The two formulas divided the spectrum between them. Wien's formula for the high-frequency end, Rayleigh's formula for the low-frequency end, and no classical theory capable of bridging them. Max Planck had been working on the blackbody problem for years, from a thermodynamic direction. On the evening of October 7, 1900, two colleagues brought him new experimental measurements of the blackbody spectrum at low frequencies. These measurements confirmed the failure of Wien's formula in that region. Within hours, Planck had written down a new interpolation formula that connected the two limiting cases and fit the complete experimental curve. He sent a postcard to one of the experimenters that same evening. At a meeting of the German Physical Society on October 19th, he presented the formula without a derivation. It was, at that point, an educated guess, a curve drawn to fit the data without any theoretical justification. The derivation came over the following weeks. It was in working through that derivation that Planck encountered the assumption he could not avoid and could not explain. To derive his formula, he was forced to treat the energy of the oscillating charges as if it could only exist in discrete units. These were integer multiples of a fundamental quantity that depended on the frequency of the oscillation. The energy of any oscillator in his derivation was not continuous but quantized. It could take the value 0 or 1 unit or 2 units, but nothing in between. The size of that unit was proportional to the frequency, scaled by a new constant that Planck determined from the fit to experimental data. That constant, now known as Planck's constant, was not derived from any existing theory. It was extracted from the data as a number that made the formula work. Planck presented this derivation on December 14, 1900, and described it privately as an act of desperation. He did not believe the quantization was physically real. He believed it was a mathematical device, a trick for counting states that would eventually be explained away. He was wrong about that. The depth of his wrongness became clear 5 years later when Einstein used the same quantization to explain the photoelectric effect. Einstein proposed that light was also a stream of discrete packets of energy. What Planck's formula describes is the competition between two tendencies that govern how energy is distributed in a hot body. At low frequencies, the energy quantum is small compared to the thermal energy available, and emission is strong. At high frequencies, the energy quantum is large, and very few oscillators have enough energy to be excited at all. The emission falls off sharply. The peak of the spectrum falls at the frequency where these two tendencies balance, and that frequency rises with temperature. The entire curve shifts upward and toward higher frequencies as temperature increases. This is why the color of heated iron shifts from red to white as it grows hotter. Red light has a lower frequency than blue light. As temperature rises, the blue end of the spectrum becomes increasingly well represented in the emitted light. The total power radiated increases as the fourth power of temperature, so the object also becomes dramatically brighter. A body at 6,000 Kelvin emits roughly 16 times more power per unit area than a body at 3,000 Kelvin. Its emission peaks in the visible range rather than the infrared. The Stefan-Boltzmann law contains within it the geometric argument for why space is cold despite stellar radiation. A star radiates its total power outward in all directions. That power spreads over a sphere whose surface area grows as the square of the distance from the star. The power per unit area, the flux, therefore decreases as the inverse square of distance. At Earth's distance from the Sun, the solar flux is approximately 1,361 watts per square meter. This is enough to maintain surface temperatures compatible with liquid water. At the distance of Jupiter, the flux has fallen to roughly 50 watts per square meter. At the distance of Neptune, to about 1.5 watts. At the distance of the nearest other star, the solar flux has become physically irrelevant. It is a fraction of a watt spread over a square meter, contributing negligibly to the thermal budget. The equilibrium temperature of a body in space is set by the balance between absorbed and emitted radiation. A body absorbs radiation from all sources, from nearby stars, from distant galaxies, and from the diffuse radiation field. When absorbed and emitted power are equal, the temperature is stable. Far from any star, the absorbed radiation comes primarily from two sources. There is the diluted light of all the stars in the observable universe, and there is a radiation field that is not stellar in origin at all, one that fills the universe with extraordinary uniformity. It arrives from every direction with equal intensity, carrying the thermal signature of the universe itself in an earlier and far hotter state. That field, and the long, slow cooling that produced it, is what sets the floor of 2.725 Kelvin in deep space. Its existence is not predicted by the physics of stars or by the inverse square law. It requires a different account entirely, one that begins not with individual stars, but with the universe as a whole. It begins with what happened in the first fractions of a second after everything that exists came into being. Before reaching that account, however, there is one place where the relationship between distance and temperature breaks down. It is a place that has puzzled solar physicists for the better part of a century. Temperature here does not decrease with distance from the sun, but increases dramatically and inexplicably. It defies the logic that the preceding chapters have assembled. That place is directly above the solar surface, in the outermost layer of the solar atmosphere. What happens there remains one of the genuinely open questions in modern astrophysics. Chapter 7: The Corona's Impossible Heat. The surface of the sun, the photosphere, the layer from which the light we see is emitted, sits at approximately 5,778 Kelvin. Rising through the thin chromosphere above it, the temperature climbs modestly. It reaches somewhere between 10,000 and 20,000 Kelvin at a height of a few thousand kilometers. This is already counterintuitive. Moving away from the heat source, the temperature is rising rather than falling. The chromosphere's warming is modest enough that it can be accommodated within existing models of energy transport. It is often attributed to acoustic waves propagating upward from the convective zone below. These waves deposit energy as they steepen and dissipate. But what happens above the chromosphere is not modest. At the boundary where the chromosphere gives way to the corona, the outermost layer of the solar atmosphere, the temperature jumps, not gradually, sharply. Within a very short distance, the temperature rises from tens of thousands of Kelvin to somewhere between 1 million and 3 million Kelvin. This depends on the specific region and the conditions. The corona is between 100 and 500 times hotter than the surface beneath it. No ordinary thermal logic accounts for this. Heat flows from hot to cold. This is not a tendency or a preference, but a consequence of the second law of thermodynamics. It is as fundamental as any principle in physics. A fire heats the room above it, not the ceiling above the room while leaving the room cold. A stove warms the pan on it, not the air a meter above while leaving the burner surface cooler. The corona violates this intuition completely. When the Swedish spectroscopist Bengt Edlén confirmed its temperature in the early 1940s, many physicists were reluctant to accept the result. His spectroscopic analysis of coronal emission lines was undeniable. The emission lines Edlin identified had puzzled solar astronomers since the 19th century. They had been tentatively attributed to an unknown element called coronium. They turned out to be emission lines of highly ionized iron, calcium, and nickel. Specifically, iron atoms stripped of 13 or 14 of their electrons. The only condition under which iron loses that many electrons is a temperature above 1,000,000 Kelvin. The spectroscopic evidence was unambiguous, and the reluctance had to give way to the measurement. The corona had been observed during solar eclipses for centuries. It is the white halo visible when the moon blocks the solar disk, extending several solar radii into space. Its structured filaments and plumes suggest a complex and dynamic medium rather than a simple atmosphere. Total solar eclipses were the only opportunity for direct visual observation for a long time. In 1930, the French astronomer Bernard Liot invented the coronagraph. It used an internal occulting disk to block the solar disk and allow the corona to be studied without the moon. But seeing the corona and understanding its temperature were different problems. The temperature measurement had to wait for spectroscopy refined enough to identify the ionization states of the emitting ions. When Edlin's analysis settled the question, it raised a harder one. What was heating the corona to these temperatures? Why did the heating intensify with distance from the surface rather than diminishing? Hannes Alfvén had been thinking about the solar corona from a different direction. A Swedish physicist with broad interests in plasma physics and cosmology, Alfvén was developing a new theoretical framework. He was studying magnetohydrodynamics, how electrically conducting fluids behave in the presence of magnetic fields. In 1942, he predicted the existence of a new kind of wave. These were transverse waves that could propagate along magnetic field lines through a conducting plasma. They carry energy from one region to another without bulk fluid motion. These waves, now called Alfvén waves, are a natural candidate for coronal heating. The sun's convective zone is in constant turbulent motion. That motion stirs the magnetic field lines that thread through it, generating waves that propagate upward into the corona. If those waves carry sufficient energy and deposit it, they could maintain these high temperatures. The energy would be deposited through dissipation, the damping of their oscillations as they interact with the coronal plasma. The difficulty is in the dissipation. Alfvén waves propagate through the corona with relatively low damping. They tend to pass through rather than deposit their energy efficiently. Various mechanisms have been proposed for how the energy might be transferred. One is resonant absorption, where waves at specific frequencies couple to local oscillations. Another is phase mixing, where adjacent field lines oscillate at slightly different rates. This generates small-scale velocity gradients that dissipate as heat. None of these has been confirmed as the dominant mechanism. The wave heating hypothesis remains one candidate among several, rather than a settled explanation. Eugene Parker proposed a different mechanism in 1988. He spent decades building theoretical models of the solar wind and the structure of the solar magnetic field. The solar magnetic field, threading through the corona, is not organized in simple, regular structures. It is braided and tangled by the convective motions at the surface. It is twisted into configurations of increasing complexity over time. Parker proposed that this tangling inevitably creates countless small sites of reconnection. Magnetic field lines of opposite polarity are brought into close proximity, and reconnection occurs. They snap into lower energy configurations and release the stored energy as heat. Each individual reconnection event is tiny, a nanoflare in Parker's terminology. But the corona contains so many of them, occurring so continuously, that their collective heating effect is substantial. The nanoflare hypothesis is attractive because it predicts a distributed, continuous heating. It would maintain the corona's temperature without requiring any single dominant mechanism. Its difficulty is observational. Individual nanoflares are too small and too brief to detect directly with available instruments. Their existence must be inferred from statistical signatures. In April 1998, the Transition Region and Coronal Explorer satellite, TRACE, began returning images. They offered a resolution and sensitivity that had not previously been available. What those images showed was a corona organized into distinct structures. Loops of plasma arched from one region of the solar surface to another, following the magnetic field. They glowed in extreme ultraviolet and X-ray wavelengths. This indicated temperatures of millions of degrees. The loops were not static. They brightened and dimmed on timescales of minutes to hours. They flickered at their foot points where they met the surface. Occasionally they erupted in bursts of energy that sent material streaming outward into the solar wind. The Yoko satellite had already established the broad structure of the corona's temperature distribution. TRACE added the fine spatial detail. It showed how that structure was organized along magnetic field lines at scales of a few hundred kilometers. The TRACE images made concrete the intimate relationship between coronal heating and magnetic field geometry. The brightest, hottest loops were those with the most complex field configurations. Regions of the corona above magnetically simple areas were cooler and dimmer. The heating was not uniformly distributed, but concentrated in the structures where magnetic energy was stored and released. This strongly suggested that the magnetic field was the energy source. The mechanical energy of convective motions at the surface was being converted into magnetic energy. It was then deposited as heat in the corona, but it did not settle the question of the specific mechanism. Both wave heating and nanoflare heating operate through the magnetic field. Both predict hotter loops in regions of more complex field geometry. Distinguishing between them requires measurements at spatial and temporal scales that current instruments approach but have not fully achieved. The Solar Orbiter mission, launched in February 2020, is providing new measurements of the corona. It is studying the solar wind at closer range than any previous spacecraft. The Parker Solar Probe has passed through the outer corona directly. It was named for Eugene Parker, who lived to see its launch in 2018 and its early results. It has sampled the plasma and magnetic field in situ at distances as close as 10 solar radii from the surface. The measurements from both missions have confirmed the presence of Alvin waves in the solar wind. These waves have sufficient energy to account for some fraction of the coronal heating. They have also found signatures consistent with intermittent reconnection events in the inner corona. Whether these observations will eventually settle the question remains to be seen. The answer may be a combination of processes operating at different scales. What the corona problem illustrates is that the relationship between distance and temperature is not always simple. The general principle holds across the vast scales of interstellar and intergalactic space. Temperature decreases with distance from a heat source as radiation dilutes, but locally, in the atmosphere of the Sun, magnetic energy can be converted into heat. This can temporarily and locally reverse that gradient. It concentrates energy in a thin outer layer rather than allowing it to dissipate outward. The corona is, in a sense, an exception that proves the rule. It requires a specific and powerful mechanism, the continuous injection of magnetic energy. That mechanism operates only in the immediate vicinity of the star. A few solar radii above the corona, the solar wind carries the material outward and it cools rapidly. By the time it reaches Earth, the solar wind has a temperature of roughly 100,000 Kelvin. This is already a factor of 10 to 30 below its coronal value. At the distances of the outer planets, it has cooled further still. It approaches the conditions of the interstellar medium it eventually merges with at the heliopause. The exception is local and bounded. The rule that stellar radiation dilutes with distance holds everywhere else. The rule that vacuum excludes conduction and convection remains. The equilibrium temperature of space far from any star settles toward a very small number. And the specific number it settles toward, not 0, but 2.725 Kelvin, requires an explanation that has nothing to do with stars at all. It requires going back to the universe itself, to the state it was in before any star had formed. All the matter and energy that now exists was once compressed into a space small and hot. The physics operating within it was unlike anything that operates anywhere in the universe today. That story begins with a piece of equipment that was never designed to look at the early universe. It begins with two astronomers who spent months trying to get rid of a noise. They eventually realized they could not get rid of it. It was coming from everywhere at once. Chapter 8: The Fossil Warmth. The horn antenna at Holmdel, New Jersey, had been built by Bell Telephone Laboratories in 1959 for a specific and practical purpose: to communicate with the early Telstar and Echo satellites that were beginning to carry telephone signals across the Atlantic. It was a large and unusual structure, a 20-foot horn-shaped reflector mounted on a rotating base, designed to collect microwave signals with minimal interference from the surrounding landscape. By 1963, the satellite communication program had moved on to more capable equipment, and the horn antenna was available for radio astronomy. Arno Penzias and Robert Wilson, both in their early 30s and recently arrived at Bell Labs, applied to use it. They wanted to make precise measurements of radio emission from the Milky Way, and the horn's low noise characteristics made it well suited for the work. Before they could do science with it, they needed to calibrate it, to account for every source of noise in the system, so that any signal they detected could be trusted as real rather than instrumental. The noise they found was not large. It was a faint, uniform hiss in the microwave band. equivalent to a temperature of approximately 3.5 Kelvin, the kind of signal that a system running at 3.5 degrees above absolute zero would produce. It arrived with equal intensity from every direction they pointed the antenna, which immediately distinguished it from any astronomical source. Galaxies, nebulae, and the plane of the Milky Way all have specific positions in the sky, and their signals vary with pointing direction. This signal did not. It was present when they pointed at the galactic plane and when they pointed away from it, present in winter and in summer, present at every hour of the day and night. It showed no variation with direction, season, or time. It was, in the language of radio astronomy, isotropic, the same in all directions. Penzias and Wilson worked through the list of possible explanations with the methodical patience of people who had built their careers on precise measurement. They checked the electronics. They recalibrated the amplifiers. They examined the antenna feed for sources of thermal emission. At some point during this process, they noticed that a pair of pigeons had nested inside the horn and had, as pigeons do, coated portions of the interior surface with what Penzias would later describe in a published paper with careful understatement as a white dielectric material. They trapped the pigeons, relocated them, cleaned the antenna, and measured again. The hiss remained precisely as before, unchanged by the removal of the birds or their contributions to the antenna's interior. They had eliminated every instrumental explanation they could conceive of, and the signal persisted. Across the state, at Princeton University, a group led by Robert Dicke and including the theorist Jim Peebles was working on a prediction. Peebles had been calculating what the early universe should have looked like based on the physics of a hot, dense initial state and what the residue of that state should look like today. His calculations suggested that if the universe had begun in a hot, dense fireball and expanded and cooled over the subsequent billions of years, it should have left behind a radiation field filling all of space uniformly, cooled by the expansion to a temperature somewhere around 10 Kelvin. Dicke's group was in the process of building a small antenna to search for this radiation when Penzias, through a chain of intermediary conversations, learned of their work and called Dicke directly. The call reached Dicke during a lunch meeting with his group. He listened, asked a few questions, and put the phone down. According to those present, he turned to his colleagues and said, with the flatness of a man watching a years-long project become immediately unnecessary, "Boys, we've been scooped." Penzias and Wilson had not been looking for the cosmic background radiation. They had not known it was predicted. They had been trying to get rid of it for the better part of a year, and what they had found, in the process of eliminating every other explanation, was the oldest light in the universe. The two groups published simultaneously in the Astrophysical Journal in 1965, Penzias and Wilson reporting the measurement, Dicke's group providing the cosmological interpretation. The signal was the cosmic microwave background, the thermal radiation left over from the period when the universe was approximately 380,000 years old and had cooled enough for a fundamental transition to occur. Before that moment, the universe was opaque. The matter filling it was a plasma, protons and electrons moving freely, too hot to combine into neutral atoms, and radiation could not travel through it. Photons were constantly scattered by the free electrons, absorbed and re-emitted, their paths randomized. The universe was, in a precise thermodynamic sense, a black body, matter and radiation in thermal equilibrium at the same temperature, exchanging energy continuously. Everything was coupled to everything else. At 380,000 years, the temperature had fallen to roughly 3,000 Kelvin, cool enough, finally, for protons and electrons to combine into neutral hydrogen without the resulting atoms being immediately broken apart by energetic photons. This transition, recombination in the technical terminology, though the electrons and protons had never previously been combined and the name is a historical accident, happened relatively quickly on cosmological timescales, and its effect on the radiation was immediate. Neutral hydrogen is nearly transparent to the microwave and optical radiation that was then dominant. The photons that had been trapped in the plasma, scattered and rescattered for hundreds of thousands of years, suddenly found that the medium around them had become transparent. They streamed outward freely in all directions, decoupling from the matter that had previously held them in equilibrium. Those photons have been traveling ever since. In the 13.8 billion years since decoupling, the universe has expanded by a factor of roughly 1100, and the radiation has been stretched by that same factor, its wavelengths lengthened, its frequency reduced, its energy diminished. What began as the thermal radiation of a 3000 Kelvin plasma has cooled, through the expansion of space itself, to the radiation of a 2.725 Kelvin blackbody. The spectrum is still a perfect blackbody spectrum, one of the most precise blackbody spectra ever measured, fitting the theoretical curve to better than 1 part in 10,000, because the expansion of the universe preserves the shape of the blackbody distribution, even as it stretches it toward longer wavelengths. The CMB is not an echo exactly, and it is not a remnant in the sense of debris. It is the original radiation field of the early universe, still present and still filling space uniformly, cooled by the universe's own expansion to a temperature only fractionally above absolute zero. George Gamow had anticipated something like this in the late 1940s, working with Ralph Alpher and Robert Herman on the physics of the early universe. Their calculations suggested that the Big Bang, a term coined mockingly by Fred Hoyle, who preferred the competing steady-state cosmology and did not believe the universe had a beginning, should have produced a thermal radiation field whose present temperature they estimated at roughly 5 Kelvin. The estimate was approximate, based on limited knowledge of the expansion history and the density of the universe, and it did not attract sustained attention. Gamow's group published their predictions. Alpher and Herman refined the temperature estimate to around 5 Kelvin in 1948, and the prediction sat largely unnoticed for 15 years, while the experimental capability to detect the signal slowly developed. When Penzias and Wilson found the radiation, Gamow was 60 years old and did not receive the Nobel Prize that Penzias and Wilson were awarded in 1978. The prize committee's reasoning for the omission has never been fully explained. Gamow died in 1968, a decade before the award. What the CMB represents, for the question this episode has been working through, is the physical floor beneath which the temperature of deep space cannot fall, regardless of how far it is from any star. A body placed in intergalactic space, shielded from all direct starlight and galaxy light, would still be bathed in the CMB, the isotropic microwave radiation field arriving equally from all directions at all times. It would absorb CMB photons and emit its own thermal radiation, and it would reach equilibrium at 2.725 Kelvin. That is the minimum temperature available to any object in the current universe. It is not set by stars. It is not set by galaxies. It is the cooled remnant of the universe's own origin, permeating every cubic centimeter of space with a patience and uniformity that no stellar source can match. The CMB is also not perfectly uniform. In 1992, the COBE satellite, the Cosmic Background Explorer, which had been measuring the CMB since its launch in 1989, announced the detection of tiny temperature fluctuations in the background radiation, variations of 1 part in 100,000 in the temperature across the sky, a pattern of slightly warmer and slightly cooler regions distributed across the celestial sphere. The fluctuations are small enough that they required a satellite with COBE sensitivity to detect, and their existence had been predicted. They are the imprint of density fluctuations in the early universe, regions slightly denser and slightly hotter than their surroundings at the moment of decoupling, which grew over the subsequent billions of years under gravity into the large-scale structure of the cosmos, the galaxy filaments, clusters, and voids that constitute the architecture of the observable universe today. George Smoot and John Mather, who led the COBE science team, received the Nobel Prize in Physics in 2006 for this measurement. Smoot described the fluctuation map, somewhat incautiously, as like seeing the face of God, a remark that generated considerably more press attention than the physics warranted, and that he later acknowledged was not his most precise statement. The CMB, then, is not merely an answer to the question of why space has the temperature it has. It is a fossil record of the universe's earliest accessible state, a thermal snapshot of a time before any star or galaxy existed, preserved in the radiation field that fills space today. Its temperature and its fluctuation pattern contain information about the density of the universe at decoupling, the ratio of matter to radiation, the geometry of space, and the seeds from which all structure grew. Extracting that information has occupied cosmologists for decades through increasingly precise measurements by COBE, WMAP, and the Planck satellite. What those measurements have confirmed, with a precision that would have seemed impossible to Gamo's generation, is that the universe began hot, has been cooling ever since, and has reached a state in which the thermal remnant of its beginning is the coldest widespread radiation field that exists. How much further it will cool, and what the universe will look like when it does, is a question whose timescales exceed anything the preceding chapters have prepared for, a cooling not over millions or billions of years, but over timescales so long that the numbers require a different kind of patience to hold. Chapter 9: The Long Cooling. The universe, 1 second after its beginning, had a temperature of approximately 10 billion Kelvin. This is not a poetic approximation or a rounded estimate. It is a calculated value derived from the physics of the expansion rate and the density of radiation and matter at that moment. and it is consistent with the abundances of hydrogen, helium, and lithium that we observe in the oldest stars today. At 10 billion Kelvin, the universe contained no atoms, no nuclei, no protons or neutrons in any stable configuration. It was a plasma of quarks and gluons and leptons, the fundamental constituents of matter, together with an intense radiation field, everything in thermal equilibrium with everything else. The temperature was so high that the distinction between matter and energy was less sharp than it becomes at lower temperatures. The cooling had already begun, because expansion had already begun. The two processes, expansion and cooling, were linked as directly as the stretching of a gas and the drop in its temperature. This relationship had governed the universe from its earliest moments and would continue to govern it for longer than any number in ordinary use can comfortably represent. By the time 1 second had passed, the temperature had already fallen far enough, to roughly 10 billion Kelvin from whatever higher value preceded it, that the universe had passed through several earlier transitions. The quark-gluon plasma had cooled enough at around 10 microseconds for quarks to bind into protons and neutrons. The ratio in which they bound was set by the temperature at which the weak nuclear force could no longer maintain equilibrium between the two, approximately 1 neutron for every 7 protons. That ratio, frozen into the matter content of the universe at roughly 1 second, determined the proportions of hydrogen and helium that nucleosynthesis would produce minutes later. Big Bang nucleosynthesis, the period during which the temperature was low enough for nuclei to be stable, but high enough for nuclear fusion to proceed, lasted from roughly 1 second to approximately 20 minutes after the beginning. During those 19 minutes, the neutrons that had survived without decaying combined with protons to form deuterium, which then fused into helium-4, with trace amounts of helium-3, deuterium, and lithium-7 left over when the temperature fell too low for fusion to continue. The result was a universe whose matter was approximately 75% hydrogen and 25% helium by mass, with lithium present at a level of about 1 atom per 10 billion hydrogen atoms. These proportions have not changed significantly since. The stars have processed some fraction of the primordial hydrogen into heavier elements through their own fusion reactions. But the bulk of the universe's hydrogen and helium is still primordial, still carrying the composition set in those first 20 minutes. The helium in the sun, the hydrogen in the water in the body of anyone listening to this, was synthesized in the first few minutes of cosmic history. It has been rearranged since, but not fundamentally altered. Georges Lemaitre, the Belgian priest and physicist who first proposed in 1927 that the universe was expanding, deriving this conclusion from Einstein's field equations before Hubble's observational confirmation, described the beginning as a moment when all the energy of the universe was concentrated in what he called the primeval atom. It was a single quantum of extraordinary density from which everything expanded. His intuition was correct in its broad outline, though the details of the very early universe have been considerably refined since his time. Lemaitre lived to learn of the CMB discovery in 1966, shortly before his death, old enough to see the observational confirmation of the expanding universe he had proposed 4 decades earlier. though not old enough to see the full implications of what Penzias and Wilson had found worked out in detail. The cooling continued through the first 380,000 years with a steadiness that the word cooling barely captures, a loss of heat so gradual, distributed through so vast a volume that any earthly analogy fails to carry the scale. At 380,000 years, as the previous chapter described, the temperature reached 3,000 Kelvin and recombination occurred. The universe became transparent. The radiation that had been coupled to the matter decoupled and streamed outward, beginning the journey that would eventually bring it, stretched and cooled by expansion, to the horn antenna at Holmdel. The matter, freed from the pressure of the radiation field that had been preventing gravitational collapse, began to gather under gravity into the first structures. Density fluctuations imprinted in the CMB began to grow, pulling matter toward the slightly denser regions and leaving the slightly emptier regions emptier still. The first stars formed somewhere between 100 million and 400 million years after the beginning. The uncertainty reflects the difficulty of observing objects at that distance and that epoch, where redshift and the opacity of the intervening intergalactic medium make detection challenging. These stars were unlike the Sun. They formed from gas that contained only hydrogen, helium, and trace lithium. No carbon, no oxygen, no iron, none of the heavier elements that stars of later generations carry. Without the heavier elements that modern stars use as catalysts in certain fusion pathways, the first stars had to rely on less efficient processes, and they compensated by being massive. They were hundreds of times the mass of the Sun, burning hot and fast through their fuel on timescales of millions of years rather than billions. Their deaths in supernovae of extraordinary energy seeded the surrounding intergalactic medium with the first heavy elements, beginning the slow enrichment of the cosmic gas that would eventually allow planets and the chemistry of life to form. The epoch of reionization followed. The ultraviolet radiation from the first massive stars and the first quasars, black holes accreting matter at the centers of early galaxies, was energetic enough to strip the electrons from the neutral hydrogen that had formed at recombination, ionizing it again. This process, which completed somewhere between 500 million and 1 billion years after the beginning, transformed the intergalactic medium from a neutral gas to the plasma it largely remains today. This is the warm, tenuous, ionized medium that fills the space between galaxies and whose temperature reflects the balance between the heating from background radiation and the cooling through radiative processes. The universe had recombined and then been reionized, going through the same transition twice on timescales, separated by hundreds of millions of years. The second time driven not by its own temperature, but by the radiation of the objects that had formed within it. Throughout all of this, the CMB continued to cool. Each time the universe doubled in size, the CMB temperature halved. The relationship is exact. The temperature of the CMB scales as the inverse of the scale factor of the universe, a direct consequence of the stretching of photon wavelengths by expansion. At a redshift of 10, when the universe was roughly 1/11th its current size, the CMB temperature was about 30 Kelvin. At a redshift of 2, roughly 3 billion years ago, it was about 8 Kelvin. Today it is 2.725 Kelvin. The cooling has been continuous and geometrically precise, a function of nothing except how much the universe has expanded and the laws of thermodynamics applied to radiation in an expanding space. The COBE satellite, launched in November 1989, was the first instrument capable of measuring the CMB spectrum and temperature with the precision needed to test whether it was truly a blackbody. Its measurements confirmed the blackbody shape to an accuracy that was, at the time, the most precise confirmation of any theoretical prediction in the history of physics. The temperature it measured, 2.725 Kelvin, with an uncertainty of a few thousandths of a degree, established the baseline that subsequent missions refined. When George Smoot presented the COBE anisotropy results at a press conference in April 1992, the map of tiny temperature fluctuations he displayed represented the oldest image of structure in the universe. It was the pattern of density variations at 380,000 years, preserved in the radiation and mapped across the sky. The fluctuations themselves, ripples of 1 part in 100,000, carried information about the geometry and composition of the universe that took years of subsequent analysis to fully extract. What COBE established, and what WMAP and the Planck satellite later confirmed with increasing precision, was that the universe's thermal history is legible. The present temperature of the CMB and the pattern of its fluctuations encode the conditions of the universe hundreds of thousands of years after its beginning with a fidelity that careful measurement can read. The current temperature, 2.725 Kelvin, is not an accident or an approximation. It is the specific value produced by 13.8 billion years of expansion applied to a radiation field that began at 3000 Kelvin at decoupling. This ratio of expansion of approximately 1,100, applied with the precision of a physical law, arrived at a number that 2 scientists at a Bell Labs antenna found as an inexplicable noise and spent a year trying to eliminate. The cooling will continue. The universe has no mechanism for stopping it, and no reason to stop. As the universe expands further, the CMB will cool further, falling below 2 Kelvin, below 1, below 1/10 of a Kelvin, on timescales that make the current age of the universe seem brief. The stars, which are adding their own radiation to the background, will eventually exhaust their fuel. The most massive stars live only millions of years. The sun has perhaps 5 billion years remaining. The smallest, most frugal red dwarf stars will burn for trillions of years before their hydrogen is spent. But even 1 trillion years is a short time against the full arc of cosmic cooling. There will come an era unimaginably distant when the last stars have gone dark and the universe's radiation background has cooled to temperatures for which no familiar analogy exists. What that era looks like and what the number 2.725 Kelvin represents in the full context of the universe's thermal history, not as a beginning, not as an endpoint, but as a specific moment in a cooling that has been proceeding since the first second, is the question the final chapter carries to its close. Chapter 10, 2.725 Kelvin. The number has a precision that rewards attention, not 3 Kelvin, not 2.5, not an approximation that rounds to something tidier. 2.725 Kelvin measured with enough confidence that the uncertainty sits in the third decimal place. The WMAP satellite, launched in June 2001 and operating for 9 years, refined the CMB temperature measurement to 2.725 Kelvin with an uncertainty of roughly 0.02 of a degree. The Planck satellite, launched by the European Space Agency in May 2009 and operating until 2013, confirmed the value and mapped the CMB's fluctuation pattern at an angular resolution and sensitivity that made WMAP's already precise measurements look coarse by comparison. 2 missions, 2 independent instrument designs, 2 separate teams of several hundred scientists each, arriving at the same number. The precision is not incidental. It reflects the fact that the CMB is among the most uniform and well-characterized radiation fields that exists anywhere in the observable universe. A black-body spectrum so clean, so free of distortion, that measuring its temperature is a matter of extraordinary care rather than extraordinary difficulty. What sustains that uniformity is the same process that produced it, the expansion of space, acting on a radiation field that was already in thermal equilibrium before decoupling and has been cooling uniformly ever since. No local process disturbs it significantly. Stars and galaxies emit their own radiation, which adds to the background at various frequencies, but their contribution to the total energy density of the CMB is negligible. The CMB's energy density exceeds that of all the starlight in the observable universe combined, because it fills all of space with extraordinary evenness, while starlight is concentrated in the relatively small volumes occupied by galaxies. The CMB is not merely a background against which astronomical objects are seen. It is the dominant radiation field of the universe, the thermal environment within which everything else exists. A body placed in intergalactic space, far from any galaxy, shielded from all directed radiation sources, would exchange energy with the CMB until it reached equilibrium at 2.725 Kelvin. This would not happen quickly. The CMB's energy density is low enough that the rate of energy exchange is slow, and a body that began at a higher temperature would radiate its excess heat into the CMB field gradually, over timescales that depend on its size, its emissivity, and its thermal mass. But the direction is fixed, and the endpoint is fixed. Everything in intergalactic space, given enough time and enough isolation from local radiation sources, converges on 2.725 Kelvin. The number is not a suggestion. It is the equilibrium temperature of the universe. This is the complete answer to the question the episode's title poses, assembled now from all its parts. Space is cold because the mechanisms that could transfer heat from stars into their surroundings efficiently, conduction and convection, require matter in sufficient density to operate, and the vacuum of interstellar and intergalactic space does not provide that density. The mechanism that does operate in vacuum, radiation, dilutes with the inverse square of distance, so that the flux from any individual star falls to negligible levels within distances that are small compared to the typical separations between stars. The equilibrium temperature of deep space is therefore not set by stars at all. It is set by the CMB, the cooled remnant of the universe's own thermal history. which permeates all of space at 2.725 Kelvin, and which no stellar radiation field, however intense at its source, significantly warms at the distances where stars are sparse. The question dissolves not into a single answer, but into a sequence of physical understandings that each depend on the one before. Heat is molecular motion. Motion requires matter to move through. Vacuum lacks the matter that conduction and convection need. Radiation crosses vacuum freely, but thins with distance by geometry. The thinning is severe enough that no star warms the space between itself and the next star to any significant fraction of its own surface temperature. The background temperature is ancient, not stellar, set by a transition that occurred 380,000 years into the universe's history and has been cooling ever since. At 2.725 Kelvin, the cooling has reached a state that feels, from a human perspective, indistinguishable from absolute zero. But it is not absolute zero, and the difference matters. Absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, is the temperature at which all thermal motion ceases, the point at which matter holds the minimum energy that quantum mechanics permits. It is a theoretical limit, approached but never reached in practice, because reaching it would require removing every last quantum of thermal energy from a system, which would require infinite time and infinite precision. The CMB keeps the universe from approaching it for now. As long as the CMB radiation field permeates space, any body in thermal contact with it has a lower limit on how cold it can become. 2.725 Kelvin, the temperature of the field itself. Objects can be cooled below this in controlled laboratory settings, using techniques that isolate them from the background radiation. But in open space, the CMB sets the floor. That floor is moving, slowly by any human measure, but measurably and continuously. The universe is still expanding, and the CMB is still cooling with it. The current rate of cooling is approximately 0.2 nanokelvin per year, 0.2 of a billionth of a degree annually. A change too small to detect in any human lifetime, but real and unceasing. Over the next 100 billion years, the CMB temperature will fall below 1 Kelvin. Over the next trillion years, below 1/10 of a Kelvin. The stars will have long since ceased to form, because star formation requires gas clouds cold enough and dense enough to collapse under gravity. And as the universe expands and its matter grows more dispersed, the conditions for collapse become increasingly rare. The last new stars are estimated to form when the universe is roughly 100 trillion years old, about 7,000 times its current age, after which the stellar population will consist entirely of long-lived red dwarf stars, slowly exhausting their hydrogen, one by one going dark over trillions of years more. After the last star, the universe will not be empty. It will contain white dwarfs cooling toward black dwarfs over timescales that exceed the current age of the universe by many orders of magnitude. It will contain neutron stars and black holes. It will contain whatever dark matter is, distributed through the volumes once occupied by galaxies. And it will still contain the CMB, cooler by then beyond any useful analogy, a radiation field at temperatures so close to absolute zero that the distinction between the two requires the full precision of quantum thermodynamics to express. The photons that decoupled from matter 380,000 years after the Big Bang will still be present, still traveling, their wavelengths stretched by the expansion of space to lengths that dwarf anything in current experience, their energy reduced to values that approach but never reach zero. The Planck satellites' maps of the CMB, released in their final form in 2018, represent the most detailed picture of the universe's thermal state at decoupling that current technology can produce. The fluctuation pattern they reveal, the slightly warmer and slightly cooler patches distributed across the sky in a specific statistical pattern, is consistent with a universe that began in a state of extraordinary smoothness, with quantum fluctuations amplified by an early period of rapid expansion into the density variations that gravity then sculpted into galaxies and galaxy clusters over billions of years. The temperature of the CMB today and the pattern of its fluctuations together constitute a document, a record of conditions that no other observation can access directly, preserved in radiation that has been traveling freely since 380,000 years into cosmic history. 2.725 Kelvin is where that document currently sits on the thermometer. It will be 2.724 Kelvin in approximately 5 billion years, when the sun has exhausted its hydrogen and swelled into a red giant. It will be somewhat below 2 Kelvin when the last red dwarf stars are cooling toward darkness. It will be a number so small that its distance from zero is measured in negative powers of 10. When the black dwarfs have finished cooling and the universe has entered whatever long, cold era follows. The cooling has no end that physics currently describes. It continues following the same relationship between expansion and temperature that has governed it since the first second, precise, patient, and indifferent to the presence or absence of anything that might be there to measure it. The stars burn. Their radiation crosses the vacuum between them and arrives, thinned by distance and geometry, at whatever surfaces it encounters. The vacuum holds none of it, conducts none of it, convects none of it. It passes through, or past, or arrives and is absorbed, but the space itself remains at the temperature the CMB sets. And the CMB settles, degree by degree across billions of years, toward a cold so thorough and so gradual that the difference between one era and the next is smaller than any instrument yet built can register in a human lifetime. Somewhere in the space between galaxies, a photon that left the surface of the early universe plasma 13.8 billion years ago is still traveling. It has been traveling since before the first star formed, before the first planet cooled, before the first molecule assembled itself from the primordial hydrogen and the heavier elements that later stars forged and scattered. Its wavelength has stretched with the expansion of the space it moves through, carrying less energy than it did at decoupling, arriving now as a microwave with a temperature signature of 2.725 Kelvin. It will continue. The space it moves through will continue to expand, and the photon will continue to stretch with it, cooler by fractions too small to name on any scale that means anything to a body lying still in a warm room. The universe outside conducting its long, unhurried business in the dark. The journey is complete. Rest well.